So a reversible reaction is one that can go in both directions. Not all reactions are reversible, but a lot of them are. So when you have a dynamic equilibrium in a chemical reaction, you have the forward reaction and the reverse reaction occurring at the same rate. The result of this, because the forward and the reverse are the same, the concentrations of reactants and products aren't changing. Because as fast as these react to form the product is reacting to reform the reactants. So there's a constant turnover, there's stuff going on, but if you look at it from a distance, the concentrations remain constant. So you don't really necessarily observe that reactions are occurring. Equilibrium is reached when the concentrations don't change anymore. This does not mean that the concentrations are equal. It just means that they're not changing. So here we can look at this example, starting with 8 of each of the reactants and 0 of the products. And over time, the reactants, the H2 and the I2, react to form products. But then as product begins to be formed, the reverse reaction occurs as well. And so you get to this point where now we've got 4 hydrogen molecules, 4 iodine molecules, 8 hydrogen iodide molecules. But as time goes on, the number of them stays the same. But they're reacting and unreacting. Does that make sense? So here's an analogy. Here we have Narnia on one side of the river and Middle-earth on the other side of the river. And initially, the population in Narnia is very high, and there's very few people in Middle-earth. So it's really crowded over here. It's kind of hard to make a living. Farmland is very expensive. So people look across the river and they're like, hey, there's land free for the taking over there, right? So initially, a lot of people are going to immigrate to Middle-earth. Is there anybody moving to Narnia here? No, because there's hardly anybody over there to move back, right? So initially, we've got this forward reaction occurring. As the population of Middle-earth becomes greater and the population of Narnia decreases, the rate of people leaving Narnia decreases. The rate of people deciding that, hey, Narnia is looking pretty good, increases, and so you get some people moving back. And so at some point, the rate of movement from Narnia to Middle-earth is the same as from Middle-earth to Narnia. Now, the population here might be larger than there, because this might be a nicer place to live. The climate might be better. Or, the natural resources are better or something. So the number of people on each side of the river is not the same. And it's not always the same people. There's people moving back and forth, but in a dynamic equilibrium, the rate of change is the same in both directions. Dynamic equilibrium.
Say 2 people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if 2 people were to bump into each other, and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. 2 molecules can join and become one. One can split apart and become 2. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now the number of limb transfers per second forward will start high and then fall. And the number of limb transfers per second backward will start at 0 and then rise. Eventually they'll meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No. Well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. Well, we're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.
Any questions? Is that helpful video? I like it.